Good morning. Welcome to my channel VSR Tech. Please subscribe my channel and click bell icon to get further notifications. My name is Raghuraman Rajasekaran. So now we are going to see the topic power factor. So in this topic, what are the objectives to discuss? In this one, power factor definition, first one, how will you calculate power factor? Disadvantages of low power factor, causes of low power factor, how to improve power factor. So these are the topics we are going to see in power factor. So next one, what is power factor? Simple definition we are giving. Power factor is nothing but a ratio between the real power and reactive power. Power factor is used to maintain the reactive power. So we can go and see what is real power, what is reactive power, what is apparent power, why we are to maintain the reactive power in the next topics. Next we'll see the definitions clearly fully. Then this is the simple definition we are given. Next one is what is power factor definitions and formulas. Normal in electrical engineering, power factor is only related to AC circuits. That is, there is no power factor in DC circuits due to zero frequency and phase angle difference theta between current and voltage. Okay, there is no phase angle difference between the current and voltage in the DC circuits. So this is mainly for the AC circuits. So, power factor definitions. This is the curve. What is power factor? The cosine of angle between voltage and current in an AC circuit is known as power factor. The theta is cos theta is called as a power factor. AC circuit, there is generally a phase difference between voltage and current will be there. So the term cos theta is called the power factor of the circuit. The term cos theta is called the power factor. In the circuit, lagging behind the voltage and power factor is referred to as lagging. That is inductive. The circuit is inductive. The current lags behind the voltage and the power factor is referred to as a lagging. Okay. So, however, in a capacitive circuit, current leads the voltage and power factor is said to be leading. Okay, a capacitive circuit, the power factor is said to be leading. Next one is how will you calculate the power factor? What is the formula? Power PF is equal to real power by apparent power. So this example also we are giving. And what is real power? What is apparent power? And what is reactive power? See. So real power means consuming power. What actual consumption of power? And apparent power is total power sent to the taken from the grid, total power. And reactive power is the wastages of power. Okay, so example, if you purchase any online product, you can get material price along with delivery charges. Okay, the material price is your, but the total cost your real power, that the total cost of the material is including with delivery charge, that is your apparent power. But delivery charge is there na, that is wastage of money only, that is your reactive power. Okay, this is simple example. So now I am showing you example, that is with the examples. Okay, load 30 kilowatt, real power, it is consuming power is 28 kilowatt. So apparent power, it is total power, that is 30 kilowatt. Reactive power, apparent power minus real power, 30 minus 28, that is the 2 kilowatt is there, that is wastage power. Okay, so formula PF is equal to 28 kilowatt by 30 kilowatt. This is 28 kilowatt is the real power by apparent power. So 28 by 30, your power factor will come, that is 0.93. This one is the power factor. So now you are clear na, in apparent power and real power, reactive power. So real power is nothing but it's consuming power, how much you are consumed. Example 30 kilowatt if you are taken means how much you are consumed, 28 kilowatt is consumed by that is the real power. So balance 2 kilowatt is there, that is the reactive power, that is wastage of power. Okay, so what as per example I am telling now, the delivery charge that you can consider, that is wastage of charge only, that is the reactive power. So the apparent power is total cost of that materials. It is including with the delivery charge. That is the apparent power. The real power is that is along total that is consuming power. Okay. So now it's clear. We'll go for the power triangle and power factor. How the power triangle is derived. You can see this one. P is equal to VA cos theta. That is the real active or true power. It is measured in watts. Same thing, apparent power measured in VA, S is equal to VI. Reactive power measured in VAR, Q is equal to VA sin theta. Okay, so we can mention instead of apparent power, we can mention how to calculate the apparent power kVA. That is, we can mention as a kVA. This true power watts now we can mention as kW. So reactive power instead of VAR we mentioned kVAR. Okay, so S is equal to root of P square plus Q square. Okay, S is apparent power is equal to root of P square plus Q square. That is, P square is your real or true power plus Q square is reactive power. So for total this unit is kW square plus kVA square. Okay, this is the formula. Phase angle, this is the phase angle. Okay, this is clear. Now we can go for the P is equal to VA cos theta. That is our formula. That is the power factor calculation formula. Cos theta is equal to P by VI. Okay, so cos theta is equal to kW by kVA. kW is nothing but that is the true power. kVA is nothing but apparent power. So cos theta is equal to kW by kVA is equal to power factor. That is a power factor. Power factor is equal to active power by reactive power. Cos theta is a power factor. So we are how we are deriving kW by kVA. Okay, kVW is active power, kVA is reactive power. Now you clear this triangle. So from this triangle, we know I told you in the first slide result, you have to maintain power factor is nothing but we have to maintain the reactive power. That reactive power. So reactive power, if you maintain properly, your power factor will get adjusted or it will maintain. Okay, so reactive power is responsible for the low power factor. So it is clear from the power triangle that smaller the reactive power component, here is the power factor of the circuit. Okay, so the main theme of the power factor is you have to maintain the reactive power. Reactive power is getting lower or higher, it will affect the power factor. Okay, so you have to maintain the reactive power. So now the power triangle is clear for you. Okay, now it's going for the next topic. Disadvantages of low power factor. What are the disadvantages of low power factor? So the power factor plays an important role in AC circuit since power consumed depends upon this factor, because the power is consumed based upon this power factor only. So the formula for the single phase supply P is equal to VL IL cos theta. IL is nothing but that is a load current. Okay, VL is voltage, load voltage. So this load current is equal to P by VL cos theta. Okay, that is a single phase supply. So for the three phase supply, root 3 VL IL cos theta. So load current is equal to P by root 3 VL cos theta. Okay, it is clear from above that this from this formula it is clear fixed power and voltage for fixed power and voltage. The load current is inversely proportional to the power factor, right? For power factor it is inversely proportional. Lower the power factor, higher is the load current. If high power factor, the load current will get reduced. Vice versa, it is vice versa. Okay, let me in following will discuss what are the disadvantages of low power factor. There is 4 disadvantages we are derived. Okay, one by one we can see with example. Okay, the power factor less than unity results in the following disadvantages. Okay, the power factor less than unity, less than 1. What are the disadvantages will come? First disadvantage, large kVA rating of equipment. The kVA rating of equipment is large because electrical machinery, example alternators, transformers, switching gears, is always written in kVA only. Okay, kVA, what is the formula of kVA? kVA is nothing but it's a apparent power, right? So kW by cos theta, kW by, that is the cos theta is nothing but it's a power factor. Okay, concept, lower power factor, higher the kVA. Power factor is getting lower, your kVA will be increase, equipment cost increases. So that I will show you in the example. Okay, load example 1000 kilowatt, voltage 250 volt, if power factor is 0.8, okay, less than unity only. Okay, so formula kVA is equal to kW cos theta. So cos theta is not, that's a power factor. Power factor is kVA is equal to 1000 kilowatt by 0.8 is equal to 1250 kVA. So for 1000 kilowatt you have to increase, if power factor is 0.8 means 1250 kVA, that rating will be increased. If it is increased means what will happen, the sizes also it will increase, so the cost will also increase, right? See, power factor is 0.9, I am increasing the power factor, so now what will happen, kVA rating will get reduced, right? So that is the example. See that power factor is 0.9, kV is 1000 kilowatt divided by 0.9, you are getting 1111 only. Okay, so kV is getting reduced. So now it is unity, if you maintain unity 1000 kVA only, so no problems, that will not, it will directly it is affecting the kVA rating. So if power factor is reduced by less than unity, the kVA rate it is increasing. So if kVA increasing means the equipment size also will get increased, and all the breakers and everything will get increased. Okay, to avoid these things we have to maintain power factor. Okay, the next one, what is the top, greater conductor size. Okay, the conductor size will get increased to transmit or distribute a fixed amount of power of constant voltage. The conductor will have to carry more current of at low power factor. This necessitates large conductor size. The electrical machine is rated in kVA because the power factor of the load is not known when the machinery is manufactured in the factory. Because when the machinery is manufactured in the factory, that time we don't know the power factor of the load. Okay, so that's why if you are not maintaining the power factor, what will happen, the low power factor will create more current in the cable, in the copper cable. So what will happen, it will get more current, so the conductor will carry more current, so this will necessitate large conductor size. So what will happen, so more current means the conductor insulation will not sufficient for the cables, so you have to increase the conductor size, that is the cable copper sizes will have to increase, and that is very big job. So to avoid these things you have to maintain power factor. So I will show you in the example. Load is 13 kilowatt, voltage is 250 volt, if power factor is 1. Okay, formula is equal to P is equal to VI. I is equal to P by V, current is equal to 13,000, that is 13 kilowatt is multiplied by 1000 divided by 250 is equal to 52 amps it is taking. Okay, for unity. Okay, same thing, I reduce to 0.6. So what will happen, kW is equal to kVA into PF, that is a power factor. kW means what, that is kW is what is that, real power is equal to kVA into power factor. So kVA is nothing but that is your this one. So 13,000. So kVA is equal to kW by PF. That is kW is real power by cos theta. That is a power factor. Is equal to 13,000 is your 13 kilowatt is 13,000, and 0.6 is equal to 21,666.7. So current is equal to, that is that how much kVA is divided by voltage, that is V. So P by V is equal to 86.7 amps. So it is taking 86 amps, 80, nearly 87 amps it is taking. So what will happen, it will increase your cable sizes and everything. So it indirectly, if the current is increasing means, first of all kVA will increase, power factor is reducing means kVA will increase. That kVA increasing means what will happen, your current also it will getting increased, the current will be getting more. If current is increased means you have to uh, uh, design the conductor sizes also. Okay, it will get increased, so indirectly the cost is very high, and then you will not you cannot maintain the standards in that one. So to maintain all the standards you have to maintain first power factor. Okay, now this is clear, you go for the third point, it is large copper losses. The large current at low power factor causes more I square R losses in all the elements of the supply system. This results in poor efficiency. Okay, what will happen? This large current, not low power factor. If it is low power factor, large current will produce. If it is large current, last I show you, na, in the greater conductor size. If large current produce means what will happen? It will get heat up and efficiency, heat up the coil, efficiency will get reduced, lifespan will get reduced, right? So this is in poor efficiency will be get poor, and then your lifetime also will not come, right? So now we go fourth point, poor voltage regulation. The large current at low lagging power factor causes greater voltage drops in alternators, transformers, transmission lines, and distributors. This results in the decreased voltage available at the supply end, thus impairing the performance of utilization devices. So what is happening here? P is equal to P cos theta. Formula is same. So I is equal to P by V cos theta, inversely proportional, right? If load current is if it is power factor is getting low power factor, what will happen? Your current will be increased. So current is increasing means voltage getting decreased. So voltage is decreases means what will happen? You cannot get you have to put a regulators to regulate the voltage. So increase the, this also increase your cost, right? So these are the four disadvantages which you are increase less than your power factor is less than unity, it will happens. Okay, so now this is clear for you. We are going for next topic, that is causes of low power factor. What are the causes? First, the main cause of low power factor is inductive load. Okay, so as in pure inductive current circuit, current lags 90 degree from voltage. Current is lagging from 90 degree from voltage. This large differences of phase angle between current and voltage causes zero power factor. If it is getting zero power factor, what will happen? So totally the current will be getting increased, right? All those, basically all those circuit having capacitance and inductance, except resonance circuit or tuned circuit, where inductive reactance is equal to capacitance reactance, XL is equal to XC. So the circuit becomes a resistive circuit. Power factor would be exist over there because capacitance and inductance causing difference of phase angle. Okay, so between current and voltage, there are a lot of disadvantage of low power factor, and we must improve power factor. So that we'll see the next topic. How will you improve the power factor? Okay, first, what are the causes? We'll see. Following are the causes of low power factor. Low power factor is undesirable from economic point of view. Normally, the power factor of the whole load on supply system is lower than 0.8. See, single phase and three phase induction motors. Usually, induction motors works at power factor, that is at full load. In full load, power factor is equal to 0.8 to 0.9 in full load. In small load, power factor is 0.2 to 0.3. No load, power factor may come to 0. This is the single phase and three phase induction motors. Usually at poor power factor, that is at full load. See, full load it is made in 0.8 to 0.9. Small load, so that's why these are the causes. So varying load in power system. So as we know that load on power system is varying. During low load period, supply voltage is increased, which increase the magnetization current, which cause the decreased power factor, right? Because if supply voltage is increased, increase the magnetization current. Magnetization current will increase, which cause the decreased power factor. Okay. Industrial heating furnaces, electrical discharging lamps, transformers, harmonic currents. These are the cause of low power factor. So how to improve power factor? How will you improve the power factor? So this is the first circuit you see. There is no nothing was the only resistor is there, inductor is there. So the circuit is like that. So we want to improve this one. We are adding one capacitor parallelly to increase the uh, improve the power factor. Okay, because capacitor is the leading circuit. So that's why we are inductor is the lagging circuit. So to avoid this one lagging, so we are adding capacitive banks. So based upon the your loads, we are adding a number of banks. That is calculation is that we will be discussed in the next topic. First, we will finish this one. The low power factor is mainly due to the fact that most of the power loads are inductive and therefore take lagging currents. Low power factor is mainly due to the fact that most of the power loads are inductive and therefore take lagging currents. Okay, understand? Because of the inductive, all the loads in this one power loads are inductive and therefore take lagging currents. To avoid this, in order to improve the power factor, some device taking leading power should be connected in parallel with the load. I show you in that figure. One of such device can be a capacitor. Capacitor draws a leading current and partially or completely neutralizes the lagging reactivity component of load current. This raises the power factor of the load. Okay, the capacitor bank will increase the power factor of the load. Okay, so thank you very much for watching my channel, watching my video. So please subscribe my channel and click the bell icon to get the further notifications. Thanks for watching.